In the previous classes, we already discussed about the optics. What is the optics and what we are going to study? We discussed about the optical path coherence and superposition principle. So in this class, what we are going to do is we are going to discuss about something which is really interesting. We are going to discuss about the color formation of that. This picture itself is very clear. We are going to discuss about the color formation on the surface of a soft. Okay. So in this picture, you can see some colors which is on the surface of soft film. Like this has happened when it is subjected to white light. We are going to study about the physics behind the color formation on the surface of a thin film. So you can see there are some colors, but white light, which means there are violet, indigo, blue, green, yellow, orange, red. Okay, there are 7 different colors, but it is 7 different colors are not present. There are some colors, some combinations are present, some are not present. So I'm going to tell you why some are present and some are absent. Okay. For that, I need you to consider this ray diagram. Here, I have a thin film which is of thickness T. Okay. Above and below we have air. This film has a refractive index mu. The air which is having a refractive index mu is equal to 1. Okay. Now, when this is the origin, I am representing it as O, which is producing, this is the origin which is producing white light. When light is incident on the surface, obviously there will be reflection as well as transmission or refraction. So a part of the light is reflected and a part of the light is transmitted. Okay. From this lower surface of the film, again there is a reflection and a transmission. This is not, we are not considering this because we are considering something which is happening above the film. Okay. This is interference by reflection. So obviously it will be above the film. And this ray is right going below the film. Okay. So we are not considering this thing. And here this is reflected, and here also there is a reflection and as well as a transmission. Okay. So we have 2 light rays. One is AP, which is the first reflected light ray. The second one is ACDE. Okay. These 2 interfere and produce the beautiful colors which is seen on the surface. Okay. So this color formation I told you, it is because of interference. Interference means superposition of coherent sources. That is interference. Okay. In order to study the interference, we need something which is very important, which is path difference. Okay. So depending on this particular thing, only we can explain interference. Okay. So here we are going to derive the equation of path. Okay. It is very simple process. You just need to listen to the class proper. Okay. So this is a very simple process. We are going to derive the equations of the general equation of path difference so that we can explain the interference. Okay. So here I told you that I am representing the path difference. I told you one ray is A, C, D, E. Okay. So this is my ray. That is A, C, D, E. The path travelled by the ray A, C, D, E minus path travelled by the ray A. Okay. The path travelled by the ray A, C, D, E minus path travelled by the ray AB. Okay. And see, in this picture, at this point A, simultaneously reflection and transmission is happening. Okay. So from this point A, AB is moving very fast. This AC is traveling little slower. Why? Because it is a thin film, it has a value of refractive index. When the density increases, what happens? The refractive index increases, the speed decreases. So obviously the ray ACDE will be traveling the bigger part. Okay, which will be covering the more distance. So here the path difference, I am representing it as D. D is equal to, what is the extra distance traveled by the light ray? That is AC plus CD inside the field. Okay. So that is AC plus CD inside the field minus AB. Okay. So here I told you this reflection and this transmission is happening simultaneously, and this reflected ray is traveling through air. Okay. So you can see the ray ACD. It is taking a certain time to reach this point D, right? In that time, what happens? The AB is also covering a certain distance. Okay. So I am repressed to get that extra distance. Okay. So from this point DE, from this point D, I am drawing a perpendicular to the ray AB. So it is intersecting at this point F. Okay. So AF is the distance traveled by the ray after reflection. Okay. So from this DE and FB will be similar, but there is an additional part, because what happens? This is happening first. Okay. So this is happening first. So the time taken for the ray to reach the point D, AD. Okay. This AB is covering an extra distance. To find that extra distance, we are drawing a perpendicular from D to AB, which is meeting at a point F. So AF is the distance which is in AB. Okay. So the path distance D is equal to AC plus CD in film minus AS in the air. So at this point I need you to remember something we already studied. Okay. What was that? It was optical path. Okay. The optical path which we already studied. What was that? The optical path is equal to the distance is equal to the distance traveled in vacuum is equal to refractive index times the distance traveled in medium. Okay. So that is the relation. So here in this equation, what? One thing is traveling in air and the other thing is traveling in film. For film, we have a refractive index mu. For air, the refractive index mu is equal to 1. Okay. So considering that, I'm writing the path difference is equal to AC plus CD into mu minus AF into mu is there, but the value of mu is 1. Okay. So AC plus CD into mu minus AF. Okay. But see, this equation AC, CD, F, which is valid, but only when we have this picture. Okay. This thing is valid only when we have this picture. So, we need a general equation. So, we need to solve for what? We need to solve AC, CD and X. Okay. Taking this AC and CD. Okay. To study this AC and CD, I am considering the triangle ACG and triangle BCG. Okay. I am taking the triangle ACG and triangle BCG. Okay. Here you can see the first thing. It has a common side which is GC, which is the thickness of the film. Okay. Also, the angle ACG is equal to angle BCG, which is R. Okay. This AD, which is bisected with this GC, therefore AG is equal to D. So from this, we have three things. This, we have GC, which is equal to thickness, angle ACG is equal to BCG is equal to R, AG equal to GD. So from these three, we can write AC is equal to CD. Okay. So we can write AC is equal to CD. So here this equation become, when AC equal to CD, D become D is equal to AC plus AC, since AC equal to CD, into mu minus AH, which is equal to 2 into AC into mu minus AH. Okay. Now what we need to find? Now we need to find this AC as well as AH. Okay. So first I'm checking for AC. To find AC again I'm considering the triangle ACG. Okay. I'm considering the triangle ACG. From that I'm taking cos R. Okay. Cos R is equal to what? Adjacent side. Adjacent side is GC. Divided by hypotenuse, which is AC. What is GC? The thickness of the column. Cos R is equal to T divided by AC. Okay. Cos R is equal to T divided by AC. So we got what? We got AC is equal to T divided by cos R. Okay. AC is equal to T divided by cos R. Now our equation D is equal to the factorization is equal to, instead of AC we have T by cos R. Substituting, we will get 2 into mu into T divided by cos R. Okay. So one side it is clear. Okay. We don't have anything AC, ABCD is nothing we have. So now we need to find. Okay. So for that, which triangle consists of AF? AF is the part of the triangle AD. Okay. So to find F, okay, we have the triangle ADF. Considering the triangle AD. Okay. So I have the triangle ADF. From that, to find AF, I am taking sine I. Sine I is equal to opposite side, which is AF, divided by hypotenuse, which is AD. Okay. And previously I told you AD is bisected with this GC. So AG is equal to GD. So I can write AF divided by AG plus GD, or sine I is equal to AF divided by 2AG. Okay. So to find the value of AF, I am taking this triangle. Sine I is equal to opposite side divided by hypotenuse, and this AD, which is bisected with GC. So the equation for sine I becomes AF divided by 2AG. Therefore, AF is equal to 2 into AG into sine. Okay. So our equation became, what was our equation? Equation was D is equal to 2 mu T by cos R minus AS. So our equation becomes D is equal to 2 mu T by cos R minus 2 into AG into sine. Okay. 2 mu T by cos R, 2 into AG into sine. Now again, here in this equation, we have again AG. Right, we have AG here. So we need to find the value for AG. Again, I am considering this triangle AG. So the triangle ACG. Okay. From triangle ACG, I am taking tan R. Tan R is equal to opposite side of AG divided by adjacent side is GC, which is thickness, which is AG into T, and I have AG is equal to T into tan. Okay. From this triangle ACG, I have tan R is equal to AG by GC, which is equal to AG by T. So AG is equal to T into tan R. So now what I am going to do, I am going to substitute this way. So I'll have the equation which is D of the so we have R is equal to 2 mu T by cos R minus 2T tan R sine. Okay. Here we are substituting for AG, which is T tan. So 2T tan R sine. Okay. So this is somewhat clear, right? here in this equation we don't have anything from the figure. We have the tan r sine I and mu thickness. Okay, but this is a bigger equation. We need to simplify this equation further. So, okay, at this point, let's recollect Snell's law. According to Snell's law, what? The refractive index mu is equal to sine I divided by sine R. Okay, according to Snell's law. And what is sine I? Sine I is equal to mu into sine R. Okay, Snell's law says mu is equal to sine I by sine R. So sine I is equal to mu into sine R. So now I am going to substitute it here. Okay, I have sine I here. Instead of sine I am going to substitute mu into sine R. So the equation becomes what? D is equal to 4 mu t by cos R minus 2t tan R. Instead of sine I have mu into sine R. Okay, I hope it's clear. Now again we are going to simplify the equation. This is the final equation we derive. So here we know that tan R is equal to sine R by cos R. So I am also going to put that here. So I get the path difference is equal to 2 mu t by cos R minus 2. I am taking the mu here. Okay, 2 mu t. Instead of tan R, I have sine R by cos R into sine. Okay, so the path difference is 2 mu t by cos R minus 2 mu t sine R into sine R divided by cos R. So here in the both this equation, in this both the equations, here we have 2, here we have 2, we have mu t. So there are some common terms, right? So I'm going to take all those common terms outside. So you can see d is equal to 2 mu t divided by cos R into, taking all these terms, we have 1 minus, I have sine R into sine R, which is sine square R. What is 1 minus sine square R? You know that sine square R plus cos square R is equal to 1. So 1 minus sine square R is equal to cos square R. Okay, so I'm going to put it here. So I'll get d is equal to 2 d by cos R into cos square R. Okay, d is equal to 2 mu t by cos R into cos square R. So here we have a cos R. Okay, here we have a cos R and we have a square here. So d is equal to 2 d. Okay, so we have the equation. We have the simplified equation from the figure. D is equal to 2 d cos R. Okay, now in this case, you can see, okay, the reflection. We have a film. This is the film. This is air. Okay, which one has the more density? The more denser means the film. That is having a refractive. Okay, air is less denser than the film. So in this case, the first reflection, this one, is happening on the surface of a denser medium. Okay, so suppose this is the surface and this is the incident ray and this is the light wave electromagnetic radiation. This is the reflected radiation. Let's remember to this. Whenever this happens, that is, whenever the reflection happens at the surface of a denser medium, what happens is, this is the surface of a denser medium and this reflection happens. These two rays, this is the first and second one is the reflected ray. One is incident, two is reflected. There will be a phase difference of pi between this one and two. Okay, there will be a phase difference of pi between one and two. So we need to include that phi also. But we have derived the equation for the path difference. So we need to rewrite that phase difference phi in terms of path. For that we have an equation that is phase difference is equal to 2 pi by lambda into delta, or delta is equal to lambda by 2 pi into. Okay, so we have the value of phi, that is here. So I am substituting for phi, I am substituting this one. This is cancelled, so I have delta equal to lambda. Okay, so the actual path difference will be delta. Okay, the actual path difference delta, which is equal to the path difference which we derived from the film minus lambda. Okay, delta is equal to 2 mu t cos r minus lambda by 2. Okay, now we have the final equation, that is the thin film when it is exposed to some kind of light. The thin film when it is exposed to some light, say white light, then we will get an interference pattern. The path difference corresponding to that interference pattern is delta is equal to 2 mu t cos r minus lambda by 2, minus lambda by 2, because this is because the light ray which is initially reflected from the surface of a denser medium. Okay, so there will be a phase change of pi between the incident ray and the reflected ray. So corresponding to the phase change of pi, we have the path difference lambda by 2. That's what is this lambda by 2 is. So this is the actual path difference of these between these two rays. Okay, this is the actual path difference between these two rays. Okay, now we derive the equation for the path difference. So the problem is not yet solved. Okay, problem is not yet solved because we are trying to find the color formation on the surface of the thin film. Okay, so for that we have the equation of path difference, that is delta is equal to 2 mu t cos r minus lambda by 2, that is done. Okay, that is the general equation we derive from the figure. And from superposition principle we have when delta equal to n lambda, it will be having a construct. Now we have the equation for the destructive interference, that is delta is equal to 2n minus 1 lambda. Okay, now when delta equal to n lambda, that is the general equation from superposition principle. Also this thing. Okay, delta equal to 2n minus 1 lambda by 2. And here we have the equation which is we derived from the figure. Okay, now we are going to equate. For constructive interference I have 2 mu t cos r minus lambda by 2 equal to n lambda. That is 2 mu t cos r is equal to n lambda plus lambda by 2. Cross multiplying we get 2n lambda plus lambda whole divided by 2, or I can write 2 mu t cos r is equal to 2n plus 1 lambda. Okay, so substituting the general equation for the constructive interference for thin film, 2 mu t cos r is equal to 2n plus 1 lambda by 2 is the condition for the constructive interference. Okay, and substituting it here, we have 2 mu t cos r minus lambda by 2 is equal to 2n minus 1 lambda by 2. Okay, therefore 2 mu t cos r is equal to 2n minus 1 lambda by 2 plus lambda by 2 equal to 2n minus 1 plus 1 lambda by 2. This cancels, we will get n. Okay, that is 2 mu t cos r is equal to n lambda. That is the condition for the destructive interference in the case of the thin film. Okay, destructive interference in the case of the thin film. Now we can simply explain the color formation. Okay, so the condition for the constructive interference is 2 mu t cos r is equal to 2n plus 1 2. And the condition for the destructive interference is 2 mu t cos r is equal to n. Okay, that is the condition for constructive and destructive interference. So white light consists of 7 different colors, right? Lambda violet, lambda indigo, lambda blue, lambda green, lambda yellow, lambda orange, and lambda red. Okay, so it has 7 different colors. That means 7 different wavelengths. All these wavelengths will not be simultaneously satisfying any of this condition. Okay, or I can say all these 7 wavelengths will not be satisfying the condition for constructive interference or the condition for destructive interference simultaneously. Okay, all those wavelengths, means out of the 7 wavelengths, some wavelengths will be satisfying the condition for constructive interference, some wavelengths will be satisfying the condition for destructive. Okay, all those wavelengths which is satisfying the condition 2 mu t cos r is equal to 2n plus 1 lambda 2 will be seen on the top of the film. Okay, suppose violet is satisfying this condition, violet can be seen on the top of the film. Suppose indigo is satisfying the condition, indigo can be seen on the top of the film. Suppose violet, indigo and blue together is satisfying the condition, all these 3 colors will be seen on the top of the film. Okay, so all those wavelengths which is satisfying condition for the constructive interference will be seen on the top of the film. Okay, and those wavelengths which is satisfying the condition which is 2 mu t cos r is equal to, okay, suppose some wavelengths are satisfying condition 2 mu t cos r is equal to n lambda. For thin film, these wavelengths will be absent. That's why there are some colors are seen on the top of the film and some colors are absent. Depending on which wavelength is satisfying which condition, which it can be seen and sometimes it will be absent. Okay, I hope you understand today's topic. I already given you the notes. Please go through the notes. Please go through the video lectures. Make your own notes. Please don't by heart this session. Understand the topic clearly. This is a very, very important essay. Thank you.